Good afternoon. I'm Catherine and I'll be your room host for today. For this session, Build an Audio Classifier on Amazon SageMaker, please welcome to the stage Emma and Anushri.
So first of all, we want to acknowledge the traditional custodians of the land on which we're meeting on, the Ngunnawal people. We acknowledge and pay our respects to the continuing culture and the contribution they make to the life of this city and this region. We also acknowledge and welcome other Aboriginal and Torres Strait Islander people who are present today. So, imagine it's 5 a.m. and you hear a sweet-sounding bird call from outside your window. Have you... Oh. Pause for bird sound.
Not sure if that came through.
Have you ever wondered to yourself, what bird could that be? Well, Anushri and I had a similar thought, and being passionate about birds and machine learning, we built an audio classification system to understand what bird was talking to us. Now, you may not be interested in birds, but you may be interested in other sounds for audio classification, such as for a production line to understand if a machine's about to break, or finding a voice in the crowd. However, audio has different rules in machine learning to computer vision. So in this session, we're going to be showing you how you can build your own audio classifier and be able to apply these classification techniques we'll be going through to your own use case. So over the next 40 minutes, we're going to be going through a bit of an introduction to the topic, why we built this audio classification system, and then how you can use audio in machine learning and the format and how you should represent it. Then we'll be going through the tools on AWS to be able to build your audio classification system. Then we'll be going through the solution we built, and then a bit of a demo. And I do just want to say, this is a level 300. We're going to be diving deep. We're going to be showing some code, but we're going to be stepping you through it.
Awesome. Thanks, Emma. Doesn't seem like my clicker is working, so if you can help me with that.
Yep, got you, girl.
You. Great, so let's talk birds. But actually, let's talk about Australian biodiversity at large and the monitoring efforts of the Australian government. So before we dive into the solution today, we'll take a look at the current state of affairs of Australian biodiversity and the monitoring efforts by the Australian government. So according to the Department of Climate Change, Energy, the Environment and Water, there are currently 486 species of Australian fauna listed in the threatened category. And according to a recent report released by this department, the Threatened Species Strategy Report, there are monitoring actions and monitoring plans outlined in this report using wildlife camera traps and bioacoustics monitoring equipment. What this report finds is that passive acoustic monitoring is less invasive to the natural habitat of certain species. So it is able to capture a more holistic presence of certain species with vocalizing behaviors, such as birds. So keeping this in mind, could we?
Yeah. Oh, yeah, give it.
This is probably better. Let's keep this in mind and consider a scenario. So here's Jane. So Jane works for the Department of Environment Planning, and she's currently involved in a suburban planning project. And for this project, Jane is currently surveying a particular region, and she needs to identify whether the threatened species, the woolly wagtail, is present in that region. So what does Jane do? Jane goes ahead. She installs some acoustic monitoring systems in the region, and she begins to record and capture audio. So once she has captured the audio, next Jane has to listen to the audio and refer to biodiversity data experts to find out whether there are any woolly wagtail sounds recorded in that audio. As you may imagine, the last couple of steps in this process, they're pretty laborious in nature, extremely manual. For example, if Jane has recorded 2,000 hours of audio data, it would take her around 12 weeks of constantly listening to this audio data and finding out whether the woolly wagtail bird song has been recorded. So Jane wonders, is it possible to improve this process? Is there any way to automate certain steps of this process? So she turns to the power of machine learning to automatically classify audio data.
So you can use machine learning with audio, but what's the best way to use it, especially for a classification system? So that's what we'll be going through now. So audio is a complex data format. it's a mix of wave frequencies with different intensities over a period of time. So there's these 3 dimensions to it. And to be able to use audio and machine learning, we need to convert it into a matrix or tabular-like data format. So how can we preserve these 3 dimensions in the transformation and represent it in a tabular format? And what is a suitable conversion? Well, actually an image. And since we're going to be converting it to image, we can use those image processing and computer vision techniques that we're familiar with. And an image is a great data format as it preserves these 3 dimensions. And through our research, we actually found that this is the most common way to do image classification, audio classification, is to convert it into an image. So what's the best image format for audio? It's actually a spectrogram. So a spectrogram is a visual representation of the frequencies of an audio signal as it varies with time. So here on the x-axis, we have time. On the y-axis, we have frequency, and then the color here is represented with the intensity. But looking at this spectrogram, there's actually quite a bit of blank space, which isn't good for our machine learning models. So there's actually an improvement to the spectrogram we can apply. And this is transforming it into a MEL spectrogram. So a MEL spectrogram is where the frequency has been converted to the MEL scale. And we can see it makes a better use of the pixel space. And so it captures the same information, but it's in a better format for our models. So, and we can see here the information's been maintained. And so we've now got our audio in a visual representation. Now let's apply a classifier to it. So just very briefly put what an image classifier is. We have this image, and we want to know what bird species it is. So our model might look at different features in it, such as the beak or the plumage, to help inform that classification. But we want to be applying it to spectrograms, MEL spectrograms. So we would train our model on a corpus of MEL spectrograms, and so it can identify what bird call it's representing. And so this is the bird call of an eastern whipbird, and you can see there's quite a distinctive shape, and we'll be actually looking at some other MEL spectrograms as well to help solidify this idea. So, as said, we're looking at some other birds. So we're going to be looking at the kookaburra, the eastern whipbird, and the willy wagtail. And these 3 birds have quite distinctive calls, don't they, Anushri?
Absolutely, yeah.
And I think this is a great time to introduce them to our audience.
Let's do that. Let's do that, and actually, we're going to get some interaction going on here, so let's play a game, shall we? So as you can see on the left-hand side of the screen, there are some birds along with some bird calls. And on the right-hand side of the screen, there are some MEL spectrograms. So your mission today, should you choose to accept it, is to match the bird call to its MEL spectrogram, right? So how we're going to do this is I'm going to play you a bird call, and you're going to take a chance at guessing what the MEL spectrogram for that particular bird call is going to look like. So we're first going to hear the eastern whipbird.
Oh. Okay, kookaburra.
That was a kookaburra. Yeah, so that was the very familiar kookaburra call. So any guesses which MEL spectrogram might belong to that call?
Sure. Oh. 2, I see some 2s.
Yeah, I hear some ones and twos. Yes, yes, absolutely. It's actually MEL spectrogram number 1. So well done to everyone that guessed number 1. We'll now hear the willy wagtail, I suppose. Sounds a bit like a cricket, so what do we think? Which MEL spectrogram?
2.
Number 2, yes, that's right, very well done. We unfortunately couldn't hear the eastern whipbird, so let me see if I can just go back and play the whipbird sound, actually. Kookaburra again. Yeah.
Oh, that's it.
That's it. So that was the beautiful whip of the eastern whipbird, so that's obviously MEL spectrogram number 3. Thank you so much for your participation in this little game, and congratulations, you're all now audio classifiers. Moving on. So with this idea of generating MEL spectrograms from audio, Let's think back to Jane's scenario and how her process can be improved with machine learning. So we had Jane. Jane has recorded hours of audio data, bird audio data, and all she has to do next is to generate MEL spectrograms with the audio that she has captured. She can then use these MEL spectrograms to train a machine learning model, which will then automatically classify audio data for her and inform her whether the willy wagtail, her bird of interest, is present in the region that she's currently surveying. Now, as you can see, Jane does not need to go through the entire manual, laborious process of listening to all the audio files and referring to biodiversity data experts. So all of this sounds great in theory, right? But let's see how we can apply this in the context of AWS. So for most machine learning use cases, AWS offers a fully managed service called Amazon SageMaker. And SageMaker enables users to prepare data, to build, train, and deploy models with fully managed infrastructure, fully managed workflows, and tooling as well. And in fact, that's exactly where we got started as well. In particular, we use something called Amazon SageMaker Studio Notebooks, which helped us build notebooks for developing the end-to-end machine learning lifecycle that was required to build out our audio classifier. And once you've identified the problem case, and in our case, that was the bird audio classifier, we then had to choose the right algorithm to do the job. So Amazon SageMaker actually contains, it provides a lot of built-in algorithm, a comprehensive set of built-in algorithms, actually. So once you've identified your use case, you can use this slide here as a little cheat sheet. So take an example problem, find out what you would like to do, and find the appropriate algorithm for you to do that job. I'm just going to pause here, let you take a photo of this. And in our case, we were building an audio classifier. However, we have now generated MEL spectrograms from the audio files, which are images. So we went ahead and we chose the image and multi-label classification algorithm that Amazon SageMaker provides built in. So let's take a closer look at the algorithm. So it uses supervised machine learning, which means that you need to know the class of the image beforehand, the target label of the image beforehand. It uses a convolutional neural network, the ResNet, and therefore it enables you to either train your model from scratch or use transfer learning for training as well. So this algorithm essentially takes an image as input, and it outputs one or more labels assigned to that image. In our use case, we were interested in a single label output, but it also supports multi-label classification as well. Finally, the input format that is accepted, and in fact most recommended for this model, is the Apache MX NetRecord.io format. However, this algorithm also accepts raw image formats such as JPEGs and PNG files. And we took that route. We generated MEL spectrograms as PNG files. We fed those PNG files into the classifier as our input. Well, finally, we are getting into the solution, the stuff that you've been waiting for so far. So let's take a look at the solution architecture for our proof of concept. So we have the audio recordings, our bird songs, which are uploaded to an Amazon Simple Storage Service, or S3 bucket. So S3 is an object storage service in AWS, and S3 is tightly integrated with Amazon SageMaker. We then have an Amazon SageMaker Studio environment, the notebooks that I spoke about previously. So we have, in the Studio environment, we have notebooks that perform different jobs, right? Different steps of the process. So we have a notebook that processes the audio files in the S3 bucket. We have another notebook for generating the MEL spectrograms. We have a notebook to train the model. And finally, we also have a notebook to perform inference. So the overall process, connecting that back to the solution architecture that I showed you, it can be broken down into 4 main steps, and we're going to go through these steps one by one now. The first step is to gather audio data, so preparing the data set required for training the model. The second step is to, of course, generate the MEL spectrograms. The third step is to prepare the data for the model in a way that Amazon SageMaker expects it. And the final and the most important step is to train and validate the model. So shall we dive into each of these processes, Emma?
Yes, let's dive into each of these steps and take you through them. So the first step, get your data. Unfortunately, we're not Jane. We don't have audio equipment to go record some birds out in the field, but we have the next best thing, which is the Atlas of Living Australia. So for those who don't know what the Atlas of Living Australia is, this is Australia's national biodiversity database, and it's actually a part of the CSIRO. And so something the Atlas of Living Australia does is store biodiversity data, and they store it in a way that's really easy and accessible to use. And something that they have to make that even easier is a R package called Galar. So here we've got a bit of R code, and we'll be taking you through how you can download some audio files of interest. So here you use the Galar call API, and then with the Galar identifier, you can say what species you're interested in. In this case, we're downloading some willy wagtail data. We can then filter for what we want from the data. So we wanted just the audio files, so we downloaded all the sound multimedia of the willy wagtail. And then with Atlas Media, you can tell it where to download it. So we downloaded it to a local folder directory on our laptops. And so we repeated this for all of our birds of interest. Remember the kookaburra, the eastern whipbird? And then we had to actually listen to the audio because there were some human voices in it and background sounds. So we needed to have we wanted to just get those bird calls, the whips, the willy wagtail calls. So we did a bit of manual cleaning of our data after we downloaded it because we need good data to train the model. Once we've downloaded it, we now need to visualize it. So on to step 2. Each of the audio files were of different lengths, so we standardized them and we just took 3-second clips within these audio files. And we did this because it makes it easier to sample it into discrete steps, and also because time is one of those factors. By standardizing it, it represents the same time frame, space of time. So we have our audio. We've sliced them into 3-second intervals. We can now visualize them. So we're going to be looking at a bit more code, but now we're looking at some Python code. And I'm going to be taking us step by step in the transformations needed. So something we're going to be taking advantage of is a library called Librosa, which is a package for music and audio processing. So the first task, import the library, and then to load it into Librosa. So we're loading in our 3-second sample clip into Librosa. We then use feature MEL spectrogram, and it'll create a MEL spectrogram of our clip. So this is the output of what it looks like. It's actually a bit hard to see on the screen, but you can sort of see a little bit of the waveform. So that's the output of feature MEL spectrogram. Now, this doesn't exactly look like those spectrograms we were showing you earlier. There's one more transformation needed. So we need to transform the amplitude to decibels. So that's the color, the intensity. And we do this because we hear sound logarithmically rather than linearly. So by converting to decibels, we can represent that, and it creates our colorful spectrogram. And so this is a spectrogram of a whipbird, and you can see that the waveform is preserved in that transformation, but it makes it clearer. And the final step is to save all these images and then upload them to our S3 bucket. So we ended up getting like 600 images, didn't we, from all of our audio?
Yep.
And we uploaded that to S3. And so that leads us to the next step.
Absolutely. So step 1, we gathered audio data. We had the amazing Atlas of Living Australia database. And step 2, we've created MEL spectrograms. So that brings us to step 3. We have our data set, but we need to prepare the data set, store the data in a particular manner in S3 so that Amazon SageMaker plays nicely with the data. And as you can see on the screen here, this is the S3 folder structure that we utilized. So we had 600 images. We split the overall data set that we had into 2 further data sets, the training data set and the validation data set. So we utilized a split of 80-20, 80 training, 20 validation. And we stored it in this structure. We stored the train data set under a folder called train and the validation data set under a folder called validate. However, we had 2 additional folders as well in S3, which are expected by Amazon SageMaker, the training list file and the validation list file. So what's a list file? A list file is a tab-separated file with 3 columns. And it essentially indexes all of the images that are going as input into the training of your machine learning model. So the list file from this snippet, there's 3 columns. The first column specifies the image index of a particular image. The second column specifies the class label index of that image. So in our use case from this snippet, we have class 0 for the eastern whipbird. We have class 1 for the kookaburra, and class 2 for the woolly wagtail. Now the third and final column specifies the relative path of that particular image that Amazon SageMaker is interested in the S3 bucket. So it's essentially the list file tells Amazon SageMaker where to find an image file either for training or for validation. And once you have done this, we come to the final step of the process, which is training the classifier and the very exciting step of validating the model. So this final process is a pretty important one, a pretty big one. So we've broken it down into 4 further steps for simplification. So firstly, we need to retrieve the container image of the algorithm that we are interested in. So we're going to take a look at some Python code. We first import Boto3, which is the AWS SDK for Python. We then use a very simple API call called retrieve to retrieve the container image of the algorithm of interest. So in our case, it was the image classification algorithm. So simply by specifying which algorithm and using the retrieve API call, you're informing SageMaker to utilize that algorithm for the training job. Second step is to train the model. So you can do this by setting some training job parameters and hyperparameters for the algorithm. So let's take a look at some more code. We create a SageMaker client definition using Boto3, which is the AWS SDK. And we use a simple API call called create training job. And create training job takes in an argument, a parameter, which is the hyperparameters and the training job parameters that you define. Now, some examples of the training parameters are, you can specify the number of epochs. You can specify the number of layers in the convolutional neural network. You can also specify the batch size of the data sets as well, among many others. Now, optionally, if you do not want to set these parameters yourself, you can use a feature called hyperparameter tuning in Amazon SageMaker, which is where you transfer the responsibility of setting these parameters to Amazon SageMaker. So once these training parameters have been determined, you can call create training job, and that kicks off the training job for the machine learning model. Third step, once your model has been trained, you can create a model endpoint, which SageMaker uses to provision resources and to deploy models. And how this is done is by defining some endpoint parameters. You give it a name, you define some endpoint configurations as well, and you use a simple API called create endpoint. Create endpoint takes these endpoint parameters defined here as an argument, as a parameter as well. So once SageMaker receives a create endpoint request, what it does on the back end is that it launches the machine learning compute resources, and it deploys the model on those compute resources. So model endpoint is created. Now it's the most exciting step, which is the validation of the model. So let's take a look at that.
Yeah, so we've chosen the most exciting part to be the demo. So we're going to walk through a bit of a demo of how you can run inference with that created model endpoint. So for the demo, I've made a bit of a Frankenbird call. So I put together 4 seconds of eastern whipbird, 3 seconds of kookaburra, and 3 seconds of woolly wagtail to see how the model performs with the classification. So let's have a bit of a listen. Oh yes, there we go.
Did well this time.
Cool, so we're going to use this as the input audio to our model endpoint, and I've got a bit of a recording. So here's our SageMaker notebook environment, Jupyter Notebook, and so you can step through the process. So the process is very similar to building the model. You have the input audio, you then need to transform that into a MEL spectrogram, and then we can run inference on it. And just setting up some imports, a few helper functions to process the audio recording, such as using stereo, so 2 inputs of the audio file. And then step 2, the make MEL spectrogram. So we saw this bit of code earlier. So we're using Librosa, and then to create the MEL spectrogram, then to convert it to amplitude to decibels, and then we're going to be saving the image. And just for our demo, we decided to just save it in a local local directory in SageMaker Studio. And then this is just an example of what the output looks like. So there's our MEL spectrogram of an eastern whipbird call. And so then this will be fed to that inference endpoint to be able to run inference. So we're defining a few variables here. So the inference categories, so this follows the order of the LST file. So eastern whipbird for index 0. And this plays a part when we run the inference because that returned value is an array of size 3, where a number of classes and the confidence associated with that class is that index. So we call the invoke endpoint of our model endpoint name, which we've just defined above in cell 143. So that's our created endpoint. And then here we've got the output, so we can see the array of size 3. And the number in that array corresponds to the confidence that that image is that class. So in this case, it has predicted it is the eastern whipbird, which is correct. That's good to see. So here we're just going to be calling those helper functions we saw, so the make MEL spectrogram and the run inference, and on our longer clip. And in this section, we also do the slicing of the 3 seconds to provide of the clip. So then we're just going to be printing out the prediction, the true class, and the confidence of it being that bird call. So here we can see the inferences coming through. And it is correctly predicting eastern whipbird at the beginning. Oh no. Oh no, it has to play the video again. Okay.
That's fine.
Oh no, we have a bit of time. But the most exciting part.
That's fine.
The results.
Yes. No. Is there a way to forward it?
No.
Okay.
Oh no.
So yeah, so what it essentially did in the end is it was predicting
we got
the
someone
results.
in tech help is helping us out. Okay.
If someone from AV could help us out,
Just a little bit more. Okay, we'll look at run inference again. Oh no. Okay. So we can see the output inference, bringing it all together. Cool, and so we're also going to be sharing some resources later that you can get your hands on these notebooks yourself, because we are just showing you snippets of them. So if you do want to build your own audio classifier, we have some resources to help you do that. And we use those as the basis of our build as well, didn't we?
Yep.
Yeah, I think from here's good. So we're going to be it's going to be printing out the predictions. Here we go, thank you so much. The predictions at the time stamps. And so we can see that it's predicting eastern whipbird at the beginning, because remember, eastern whipbird, kookaburra, and then willy wagtail. But we do see there are some misclassifications, and I'm going to be highlighting that. And we can see it's actually in those transition times, so between when it moves from the eastern whipbird to the willy wagtail, eastern whipbird to the kookaburra, for example. So those times where it was changing the bird call. Anyway, we're going to dive a bit deeper into the results, but that's how you can run inference with your created SageMaker endpoint.
Great. So that was the process pretty much end to end. We utilized SageMaker Studio Notebooks to do all of this. And while we are working hard towards publishing all of the notebooks and all of the code that you just saw, they were actually very small snippets of the entire code that we utilized. We are working very hard towards publishing them to SageMaker example ourselves. In the meanwhile, though, you can scan this QR code to access AWS's GitHub repo called SageMaker Examples. And SageMaker Examples, in fact, it has a sub-repository. It's called Introduction to Amazon Algorithms. And scanning this QR code will actually take you to the image classification algorithm. And it provides a wonderful starting point. And in fact, that's how we got started as well. So we took inspiration from some of the code reference available in this repository, used it to our use case, and you can do the same as well. So you must be curious, how did our model perform? So let's take a look at the results. So we ran the first run of the validation against our validation data. So remember, we split the overall data set into training and validation 80-20. So we ran it against the validation data, and we obtained an accuracy score of 97%, which is not bad at all. And this confusion matrix, this central diagonal here with the green cells highlighted, represents the number of images that our classifier classified correctly. So as you can see, did really well on the eastern whipbird, did really well on the woolly wagtail, but there were some misclassifications of the kookaburra. But we wanted to take it a step further. We wanted to curate a brand new data set, test our model against a brand new data set. So we went ahead, gathered some more audio data, called this the test data set, and these were the results. So we had an accuracy score of 94% this time, and this time our model did really well on the kookaburra calls, but there were some misclassifications in the eastern whipbird and some misclassifications of the woolly wagtail. So this is just the beginning of what's possible. We went ahead, we built a proof of concept with limited data available, and as Emma mentioned before, we had only about 600 images generated from the audio files that we could gather, and we had 600 images across the 3 classes, and if you were to do this in production, your results may vary, right? And you might work with a larger data set, you might work with a larger number of audio files, generate a larger number of MEL spectrograms as well. So that brings us to, what do we learn through the process? Like key takeaways, some key takeaways are highlighted on this slide. We learned that audio monitoring in applications related to environment, it is low cost and minimally invasive, but this could be extended to other industries as well. So it could be really applicable to industries such as healthcare, manufacturing, mining as well. And what's really cool about audio classification is the ability to use image processing techniques to audio. So you have your good old computer vision and image processing techniques that you might already be familiar with. So you take your audio files, you generate the MEL spectrograms, and use the good old image classifier. We also saw how easy it is to get started with Amazon SageMaker. So we have great resources available. So I showed you the GitHub repo, SageMaker examples with lots of code references. And of course, there is Amazon SageMaker's publicly available documentation that you can leverage as well.
And yeah, I think as Anushree said, there's lots of resources out there to help you get started. You just need that idea to get building. And those aren't the only resources, and hopefully today and at the rest of Summit, you've been really inspired by the stories that have been told, and you want to continue your learning. Well, you can with AWS Skills Builder, where there's over 500 free courses. And once you build your skills and confidence, there's also AWS certifications, which are industry-recognized certifications, and these really help you validate and your AWS knowledge, skills, and confidence. And recently, I actually did the machine learning one, which was really valuable for me to learn about the machine learning concepts and then also how to apply them on AWS. So I do really recommend checking those out. So thank you so much.
Yep.
We've had a lot of fun putting this together, and I hope others enjoyed the session as well. If you want to continue the discussion, please feel free to come find us. We'll be around, or take note of our emails, reach out.
Yep. Sorry for the loud kookaburra sounds.
A few times as well.
A few times as well. But yeah, come find us. We will probably be hanging around at the expo hall. And if you want to have further discussions about audio classification and more details on how we got started, very, very happy to have a discussion with you all.
And please do the survey.
Absolutely.
If you haven't already, download the mobile app and find our session. It's INV302. Let us know how you found it. Feedback's really valuable to us, so really appreciate the feedback, any feedback.
Yes. Thank you.
Thank you so much. There is a bit of, should we see if there's questions? Is there any questions since we have
Yeah.
like 4 minutes?
Yeah.
Any questions? Oh, we have a question.
Yes.
In my experience, when you do image classification, one of the most challenging parts, so you see maybe small objectification, is the labeling. So you have to pop in 600 instances, right? Did you just do the manual using 3 content files, or did you do a bit more fancy labeling based on the images that you had? Just curious how you did that. How would you do that at scale? I think I know what you're going to say, but I'm just curious.
Yeah, so how we did it, so we had our bird audio downloads, and then when we created the MEL spectrograms, we knew the target class of that image, so we knew that was a Kookaburra call. So then we put that under the Kookaburra folder. So then and we only did one, so we just classified the image. We weren't picking up parts of the image to be the call. So we just said, this image is a Kookaburra call. And then the target class was known when we created the data.
Yes, so in short, it was manual.
Yeah, it was manual, but
We worked with a limited data set. However, you can utilize ground truth if it is a larger data set.
Yeah,
and
true.
Yeah,
Yeah, you could do ground truth for
yeah,
yeah. So anyway, so we knew because we downloaded the data from ALA, we knew what bird call it was to start with, to train the model, and then when you run inference on it with new data, be able to pick up things. Anyway, does that clarify? Yeah, and in production, ground truth. What else?
another
Oh,
question.
another question.
For the misclassified one, was there anything particular about the audio samples that made them misclassified, or was it just a nature of the algorithm? Did you go back and listen to them? Was there anything about them?
Yes, I did go back and listen to a few just to understand, okay, why is it misclassifying it? There were, as much as we tried to clean the data, there were, obviously birds, they sing in unison. There were overlapping bird calls that sort of confused our classifier. That was my experience.
And I'd also say, so we did this rolling window of the 3 seconds. So we went from 0 to 3 seconds, 0 to 0.5 to 3.5 seconds. So I think also those tail ends of the calls, so we would have called that a Kookaburra, but it may have only had like 1 second of a call or something in it. So I think that might have also played a part. We probably could go look at all the images in the training for the model and make sure that they were all had a good chunk of call in them.
Yeah, but our intention was to show the art of the possible, that, this is possible. And yeah, refinement, I guess, comes later. Yeah.
So when you just mentioned before that you cleaned the data, was that on obviously not the training, but the results? So, out in the wild, when you captured the audio to put it against, did you clean that data?
We did not capture any audio data, actually.
Oh, sorry, from the
Yeah.
data that you got.
Yeah.
Yeah.
Yes. Yes.
So you cleaned that.
No, so we just had like a raw, we didn't have like human voices, but
Yeah.
it had background noise and things.
Yeah, leaves rustling in certain bits, and I don't know. Most of the audio data that we found also had, someone announcing, okay, this is the bird call. So we got rid of all of that stuff, and we kept the actual calls that mattered to train our model, and we kept those sections, and then we did the rolling window of 3 seconds and trained our model using the rolling window.
The reason why I asked is, what about background noise or static and the like? I live on the back of a range
Yep.
state, so there's lots of bird calls and stuff, but then you've also got traffic at certain times. Like, how would that model work against audio?
Yeah, that's actually interesting. During the first ever iteration, we sort of also tried to model the background noise as a separate class as well, just to try how our classifier, if it can't classify it as a kookaburra, willy wagtail, or an eastern whipper, to see if it can classify it as background noise when it doesn't identify. But I guess that comes down to the confidence level that you pick finally, where you're saying, okay, yeah, this is my cutoff, like 70% confidence kookaburra. So I guess you can work with that technique and then improve your classifications in that sense.
Cool. Okay, we'll get off the stage. The
Yep.
next session's up. So thank you so much.
Thank you.